Yeah. Oops. Yes, it seems it works, judging by these strange echoing sounds. Yep. Well, I have a strange feeling like this.
No, it's not. Maybe you can try this one.
Or we can probably somehow shut down the speakers. No? Okay. Let's try this one. Though it sounds nice, in fact.
Yeah, I'm not sure for 2 hours.
Okay. So, well, the fantastic sounds are gone, and now we can continue. Okay, so thank you, Murhaf, for the introduction. And yeah, I will talk about what embeddings, which is pretty obvious from the from the introduction slide. And of course, because the lecture is quite short, I don't hope to cover all the aspects of modern distributional models, of modern web embedding models. So it will be just like a brief overview of the things which, at least for the recent years, the things which lie in the foundation of almost all natural language processing tasks. Okay, so this is kind of a picture which explains why we should care about web embeddings. This plot shows the number of papers which mention the words web embedding in their titles in the recent years. So as you can see, somewhere around the years 2013 and 2014, there happened something which strongly increased the number, which strongly increased the amount of research devoted to web embeddings and distributional models in general. And I will describe these events and just what happened. And anyway, as you can see from this plot, this surge is still increasing. So the number of papers which do something with web embeddings is still increasing, and in fact there are many more papers which do not mention the word embedding itself in their title, but which still use this. Yeah, so the people are using this extensively, and if you hope like to do something related to natural language processing, natural language understanding, computational linguistics, then web embeddings are like the necessary tool in order to use this. So we want like one of the major aims of natural language processing and computational linguistics is to somehow like to build artificial intelligence. Yep, we want to build a machine which imitates human brain, which thinks like humans, and among other things, this machine should understand the meaning of words like we do. How can we design such a machine? Yeah, so there are many ways to do this, or at least many imaginary ways to do this, and this lecture will be about one of such possible ways. So as you already know, because you already have a lecture on vector space models of meaning, we have at least one way to teach a computer the meaning of individual words, and this way is called vector space models of meaning. Yeah. So and this is kind of a brief gist of the whole lecture. Yeah. This slide kind of is a short summary of the whole lecture. So we have vector space models of meaning, and they were here like for decades. But in the recent years, we saw some advances in machine learning, which allowed us to train new kind of distributional models, and which allowed us like to achieve state-of-the-art results in many natural language processing tasks. Well, the whole landscape of computational linguistics actually has changed like approximately around the years 2014, 2015 maybe. And now people use these new kinds of models both in academic research and in practical applications, in industry projects, almost everywhere, in every imaginable natural language processing task which you can think about. Oops. Yeah, and the success of these models is based on their ability to accurately grasp and to be able to calculate semantic similarity between words, to calculate whether these two given words are semantically similar or not, and how strong is this similarity. Yeah, if you are bored during the lecture, you can like try our web service, which is dedicated to distributional models and to word embeddings. So it works on your mobiles as well. So you can just entertain yourself in case you're bored. It allows you to like explore word embedding models for English and for Norwegian. The model for Norwegian is a bit worse, but still. So you can like play with it, find out nearest neighbors for some for any word that you invent, like find out, calculate semantic similarity between pairs of words, build two-dimensional maps of how words are related to each other, and various other things. Yep, so you can try this. Okay, so what are the linguistic foundation of distributional semantics, and what is distributional semantics after all? You are supposed to know this, but I'm just will like give a brief repetition so that like to make sure that we are on the same page. So it's known that computational linguistics is very good in covering and modeling the lower tiers of language, like how words are spelled, what is called graphematics in linguistics, how words are pronounced, phonetics. We can model how words inflect, morphology, and we can more or less accurately model how words interact in sentences. That is, we can model syntax. We can build systems which automatically parse sentences into syntactic trees. Yeah, and to model means that we are able to represent some important features of some phenomena. Like in this phrase, the judge sits in the court. We can tell that the word judge, like it consists of 3 phonemes. It is a singular noun in the nominative case. It functions as a subject in the syntactic tree of the sentence, and so on. So these representations tell us lots about the word judge, but not about its meaning. Yeah, we know that we know the length of this word, we know its syntactic function, its morphological properties, but it tells us nothing about what does it mean. Yeah, just what objects in the real world come to our mind when we hear the word judge. So the question how to represent meaning is hard, is difficult, and especially to represent formally. And if we want computer to understand semantics, it means that we need some word representations which computers will be able to read, which means that that words which are similar in their meaning should be similar in their representations, in their mathematical representations. So we should somehow tell the computer that judge is similar to court, but not to kludge, though their surface forms are quite similar. Judge and kludge sound very similar, but the meaning is quite distinct. So why is this so? Why is it so difficult? Primarily because of the thing which is called arbitrariness of a linguistic sign, which means that unlike the road signs, the words in words we do not observe a direct link between the form and the meaning. We know this well. since the lectures of Ferdinand de Saussure in the beginning of the 20th century, and an example of this can be shown with the concept of lantern, which can be expressed by any sequence of letters or sounds in different languages. So it can be a lantern in English, Lukt in Norwegian, lampa in Russian, lucerna in Latin, or garel in Mongolian. And all these sequences of letters or sequences of phonemes represent one and the same meaning. So it seems there is no direct connection between the surface form and the meaning, unlike in morphology, for example. So we can extract morphology of words from surface form, but not meaning. What can we do? Like, how can we model meaning based on what data we can use to model semantics of words? Distributional hypothesis comes to our help, and basically, distributional hypothesis tells us that meaning is in fact the sum of contexts of the word. So a meaning of the word is just the sum of all contexts in which we saw this word. In fact, it can be extended even like to our brain. We can say that the meaning of words in our brain is just our memory of all the situations in which we heard this word. And it seems that the differences in contexts should be enough to explain semantic differences between the word. So between words. So words with similar contexts should have similar meaning. Yep. And in fact, the hypothesis is quite old, but it was like strictly formulated probably in the middle of the 20th century. And there is a famous quotation by Firth. You shall know the word by the company it keeps, which is kind of a. It became kind of a phrase which always comes to your mind when you think about distributional semantics. Yeah, and distributional semantic models in modern computational linguistics are built upon lexical co-occurrences in large training corpora. So we can extract contexts of the words, the co-occurrences of the words from large corpora, which we have now, fortunately. Okay, so this is kind of one of the fathers of distributional semantics. Paradoxically, this person is not was not a linguist. He was a psychologist, Charles Osgood. He developed the thing called semantic vectors, which we use until now, and which I will describe in the following slides. So we achieve to represent the meaning of particular words by vectors of real values, which are derived from frequencies of co-occurrences of these words with other words in the corpora, in the real language. So the words themselves, or their lemmas, for example, are points in this vector space, and at the same time, these same words are the dimensions of this space, which means that the semantic space of the language is represented by a matrix, a symmetric matrix in which the rows are words and the columns are the same words. Yeah, so the number of the number of rows and the number of columns is the same. Yeah, so each word is represented with a vector, and this vector is just the number of co-occurrences of this word with all other words in the vocabulary of the corpus. Yeah, like the word A co-occurred with the word B 5 times, with the word C 6 times, with the word D 0 times, and so on and so forth. Yeah, and the result is that the words with the similar contexts are closer to each other, and it tells us, hopefully, that these words are semantically similar. So in this picture, we see a three-dimensional space, but of course, with real corpora, the dimensionality will be like hundreds of thousands because the vocabulary, the number of distinct words in large corpora is like can be hundreds of thousands or millions of distinct words. And this is a problem. The fact that there are so many distinct words in human language is a problem, because it means that each word is represented by a very large vector, very high dimensional vector, like millions of dimensions, or even hundreds of thousands of dimensions. It's still a problem. It's still very difficult to manipulate such vectors. But the good thing is these vectors are sparse, which means that most components are zero. And this is intuitively quite understandable because most words do not co-occur with each other. If you just imagine two random words from your native language, most probably they quite rarely co-occur with each other in real language. So human language is not chaotic. It's the words in human language are not uniformly distributed. They tend to cluster into some like semantically meaningful groups, which means that most words in the vocabulary do not occur together. And if these vectors are sparse, it means that we can invent some ways to reduce their size to some like smaller dimensionality, which will allow us to manipulate these vectors more easily, while still retaining meaningful relations between these vectors. Well, mathematics knows many ways to reduce the dimensionality of vector matrices, and I will mention some of them. But just it's important to understand the main idea that it's a problem that lexical vectors, semantic vectors are high dimensional, and we want some ways to squeeze them, like to squeeze this 1 million dimension vector into a vector of, for example, dimensionality 300 or 100, but still keeping the fact that that the vectors for semantically similar words are similar. And such dense squeezed vectors are called word embeddings. So this is what the word embedding actually means. Yeah, something which is embedded, squeezed. So this is the topic of the lecture, in fact. And this is an example of a 300-dimensional vector or embedding of the word tomato in the model trained on British national corpus. Yeah, so you can easily see that it has 300 dimensions, and my question to you is just to make sure that we're on the same page. What values can the components of this vector take? Real numbers from what to what? In what range? From 0 to infinity? -1 to 1, of course. Yeah, so you can see that, well, in this particular embedding, like the lowest value is about -0.15, and the highest value is about like 0.14 maybe. But in theory, usually we normalize our vectors, and their components can take values from -1 to +1. This is convenient, but well, in theory, of course, your vectors can take the components of your vectors can take, well, any values that you want. But in practice, people usually normalize their embeddings so that they are like in the range of -1 to 1. And yeah, so you can represent a word either with just, or well, you can represent the vector of the word either with just a list of a list of digits, a list of values, or you can visualize it like this. Yeah, just and on such plots you can quickly see just what components of the vector are high and which ones are low, which are strongly expressed and which are not strongly expressed. And this is also the 300-dimensional vector of cucumber from the same model. Well, probably visually it's not quite clear at once that they're similar, but if we look, for example, at the vector for philosophy, it probably can be seen that it's quite different. Yeah, even from just looking at the visualizations. But of course, we have some ways of strictly proving that tomatoes are more similar to cucumbers than to philosophy, and these ways are this way is called cosine similarity. So the semantic similarity between vectors. The similarity between vectors is usually measured by the cosine of the angle between these vectors. So as the angle between the two word vectors is growing, similarity lowers, and as the angle lessens, similarity grows. This is the formula. It's in fact just a dot product of normalized vectors. So like this is the vector of the first word, the vector of the second word. This is the norm of the vector of the first word and the norm of the vector of the second word. This is the cosine similarity. Or you can just measure the angle, of course, and then calculate the cosine. Yeah, but probably the simpler way is just to normalize vectors and to calculate the dot product. And of course, all the modern mathematics libraries like NumPy or something like this, of course, have functions to calculate cosine similarity. So if we actually calculate cosine between the words tomato and philosophy, it will be like 0.09. Between cucumber and philosophy, it will be somehow higher. So it seems that cucumbers are more like philosophical than tomatoes. So it will be 0.16. And the cosine between tomato and cucumber, as you can expect, is much higher. It's like 0.66. Which means that the model actually tells us the right things. Yeah, it tells us which words are more semantically similar to each other and which words are less semantically similar to each other. You can think about the notion of cosine similarity as like you can imagine it geometrically. So if two vectors point at exactly the same direction, then the cosine will be 1. It will be at its maximum. If two vectors are orthogonal, if they are just like this, then the cosine similarity will be 0, which will mean that two words do not relate to each other in any way. They are just about absolutely different things. And if two vectors point at the opposite direction, directions, then the cosine will be -1, which like hopefully it should, well, it should in theory tell us that these words are antonyms, that they have antonymic meaning. But in fact, things are more complicated than that, and in practice, you rarely meet vectors which really point at the opposite directions. So in real models, in fact, cosine similarity quite rarely gets below 0. There are some reasons for that, but I will not spend time on explaining them. But you can, I can give you references for that if you want. Yeah, and of course the embeddings are high dimensional. The vectors are like 300 dimensions each, and we can't hope to visualize all 300 dimensions because people are limited beings and we can't imagine a 300 dimensional space. But there are ways to project these 300 dimensional vectors into two-dimensional, three-dimensional space, so that we can see kind of a glimpse of how really this semantic space looks like. Like in this case, yeah, we can take the 300 dimensional vectors of these words from the model and project them into two-dimensional space. And like we can see that the Swedish cities are in one place, yeah, like the Norwegian cities are in another corner of the plot. Yeah, the university and student are here, and so on and so forth. So in fact, such projections can be quite useful. Yeah, you can use them to quickly see what are the relations of the words in this particular model. It's kind of a map. Yeah. Yeah, and this particular projection was built using the algorithm which is called TSNE, which is quite popular nowadays, and it's an algorithm of reducing dimensionality of high dimensional vectors so that you can easily visualize them while still retaining the relations between them. Okay, so just a brief recap of what we have covered until now. So we have distributional models, which are based on distributions of word co-occurrences in large training corpora. So they're called distributional because we look at distributions, how words are distributed. They represent words as dense lexical vectors, which are called embeddings. You can also say that the models are not only distributional but also distributed, which means that each word is represented as like multiple activations. So distributed means that each of the components of each of these 300 components tells us something about the meaning of the word. It's not that only one component has some meaning. All of these 300 components or 100 components, just whatever size of the vector your model has, each of them has something to tell us. This is why we call these vectors dense, because there are no zeros, no space is wasted. Yeah, and another way is to call these models distributed. Like the meaning of the word tomato is distributed across all these 300 dimensions. There is no such thing as, for example, a dimension which tells us that this word is tomato, because of course then we will be able to represent only 300 words. No, the things are more complicated, and that's why we can represent like hundreds of thousands of words using like 300 dimensions. Yeah, but it also means that the particular vector components, like for example the vector component number 1 or number 50 or number 139, these particular components do not have like their own meaning. They're not directly interpretable. It's rarely the case that you can say that, for example, if the component number 100 in the word in some word is strong, its value is high, then this word is, well, it denotes something to it, for example. It's rarely the case. Usually, like the semantics of natural language is strongly distributed, strongly dispersed across many components. So you can probably say something like, if the components number 5, 6, and 258 are strongly expressed, and at the same time the components number that and that are weakly expressed, then probably this word denotes something to it. But in fact, in practice, it seems that most like semantic concepts of language are dispersed across like tens or even hundreds of components. So it's really difficult to discern just what where is this particular meaning in vector. So it's a problem from like a purely academic point of view. We can't directly interpret these vectors, but it's quite okay from practical point of view. I mean, it doesn't matter for us that we don't know where is this food meaning in these vectors, because if we are able to tell that tomato is similar to cucumber, then well, we're okay with that. So as long as these vectors are useful for practical tasks, well, we can go on with the fact that they are not interpretable. Yeah. So as I've already said, words occurring in similar contexts have similar vectors, and such models, of course, by definition, allow us to find for any given word which is present in the vocabulary of the model, to find its nearest semantic associates or semantic neighbors, like by just calculating cosine similarity between the given word and all the other words in the vocabulary. Like, for example, nearest associates, nearest neighbors for the word brain from a model trained on English Wikipedia will be something like cerebral with the cosine similarity 0.74, cerebellum, not even sure what this means, with cosine similarity 0.72, brainstem, cortical, hippocampal, and so on and so forth. So as you can see, the nearest neighbors are quite meaningful. So like they really kind of tell us what the word brain is about. Yeah, so they kind of, it's not a dictionary definition, of course, but well, it gives us an idea like to what semantic group, to what semantic field the word brain belongs. And it works with multi-word entities as well. So you can before compiling your model, you can like merge multi-word units into one unit, and then, for example, you will have a separate vector for Alan Turing, and it will have neighbors like Turing, Charles Babbage, mathematician Alan Turing, pioneer Alan Turing, on computable numbers, which is one of the papers by Turing, and so on. So in theory, nothing prevents you from doing the same thing with the phrases, not with the single words. And this all is extracted just by the fact that some words co-occur with each other more often than with other words, which is quite fun, I think. Yeah, so once again, you can try this yourself at this web service. You can check whether my examples are correct. Yeah, question?
We extend this model to all languages at the same time, meaning we put all the words of all the languages together.
You mean, yeah.
Making work the different algorithm and able to find, for example, close meaning between a word in Norwegian and a word in English or in French.
Yes, we can do this, and there is a whole there's a large field of research into the thing which is called cross-lingual word embeddings, when people train word embedding models on corpora from several languages at once, or sometimes on parallel corpora. And yes, then you have a model which can tell you that the words licht in Norwegian and lantern in English are semantically similar. Yeah, we can do this. I will not cover such models in this lecture, but yeah, you can easily find papers on that, or I can send you the links if you want. Okay, so how can we produce word embeddings? Oh, and by the way, should we have break at 11 or at 11? Okay, then we still have 10 minutes. The question is, yeah, how exactly do we like come to these wonderful word vectors? How can we produce them? The classical way of producing such dense vectors from large co-occurrence matrices is like we just create large co-occurrence matrix with the numbers of times that individual words co-occur with each other. It's still very high dimensional. Then we somehow scale these numbers using any scaling methods, for example, pointwise mutual information. And then we factorize this matrix using singular value decomposition, or SVD. And SVD is just one of the methods that mathematics has to reduce the number of dimensions in matrix while still retaining the similarity, the distances between the rows of the matrix. And this kind of models is called count-based models because we first have to actually count the numbers of co-occurrences for all the words. Another kind of models, the models of the kind which I will cover today mostly, is called the predictive models or predict models, and they use some kind of machine learning, usually artificial neural networks, and they were introduced first by a rather famous guy called by the name Benjo in the beginning of the 21st century, and then popularized by Tomasz Mikolov with his famous bot2vec tool, which I will describe in a while. So it has two main algorithms: continuous bag of words and continuous skipgram. Later I will cover each of them in detail. And we have lots of other ways, lots of other well-known algorithms to produce dense word embeddings, like global vectors, GLAF or fast text, and many other ways. But just the main idea of all of them is that you somehow assign each word in the training corpus a meaningful vector representation. And the last approaches, like the second, the third, and the fourth, became very popular in the recent years. As I've said, they revolutionized the field of natural language processing, and their principal difference from this first classical method is that they actively employ machine learning. So this is the workflow of a traditional count-based distributional model without any machine learning. So we just compile full co-occurrence matrix on the whole corpus, count all the co-occurrences. As I've said, we weigh them, scale them with, for example, pointwise mutual information or dice or any other scaling algorithm. Then we factorize the matrix, and in this way we arrive from sparse to dense vectors, and then we can use them in any applications. You can probably heard about methods like latent semantic indexing (LSI) or latent semantic analysis (LSI). LSA. They were quite popular, like maybe 10 years ago, and still remain popular nowadays, though maybe a bit less. And they actively employ this workflow. But this is not the topic of today's lecture. Today we will talk mainly about prediction-based distributional models, which are based on machine learning. Well, I suppose everyone here knows what machine learning is. I mean, I don't have to give long explanations about it, but just in general, some problems are so complicated that we can't just invent a chain of rules to cope with these problems, because we do not know how we actually do it. Like, I mean, we can't, for example, we can't tell how our brains tell us that tomato is more similar to cucumber than to philosophy. We can't just write an algorithm how to do this. Somehow our brains are able to do this, but we do not know how. That's why, yeah, to solve such problems, we can use machine learning, and we can attempt to build a program which learn from data, to build programs which learn from data, and improve with experience, improve with more data. Yeah, so, and artificial neural networks is one of the most popular and fashionable and trendy machine learning methods nowadays. And the methods about which I'm talking today are based on very simple artificial neural networks, very shallow artificial neural networks. And I think now it's a good time to make a short break, and after this continue with the prediction-based models. Thanks. If you have any questions, feel free to ask. Okay, so let's continue. We still have lots to cover. Okay, so how can machine learning help us to build word embeddings, to build good distributional semantic models? As I've said, distributional models built on using machine learning are often called predict models, and I will now explain why. What do they predict? So, as you remember, in the count-based models, we count the co-occurrences of the word, of all the words in the training corpus, and then we use these co-occurrences as word vectors, maybe after dimensionality reduction. In the prediction-based models, it's vice versa. The whole process is is inverted. We try to find for each word such a vector, or to learn such a vector for each word, such an embedding, that it's maximally similar to the vectors of the words which occur near this word, and minimally similar to the vectors of the words which do not seem to occur somewhere near this particular word. So it's not that we first count the co-occurrences and then try to extract meaningful vectors from them. It's that we try to learn these vectors from scratch, yeah, without counting, without building this large co-occurrence matrix. And if we use artificial neural networks for that, such learned vectors are sometimes called neural embeddings. You can sometimes see such a term somewhere in the papers or in the web. That's the history of the method. So in the year 2013, Tomasz Mikolov, who then worked at Google, published a paper which was called Efficient Estimation of Word Representations in Vector Space. Well, in fact, he was not the only author of the paper, but he was the first one. And they also made available the source code of the tool that they used to train word embeddings. The tool was called What2Vec and became very famous then after that. So this tool just implemented the algorithms from this paper. And they also published a distributional model, a word embedding model, trained on very large Google News corpus. And this model was very good. So it was very good in different tasks. So yeah, this tool called What2Vec, its source code still can be found at this address, though the tool itself seems to be a bit deprecated now. I mean, it's not actively developed anymore. But the idea itself was implemented in many other tools. Yep, in fact, what Mikolov did, he didn't invent something completely new. There are no like groundbreaking inventions in this paper. He just modified some algorithms of using neural networks to train word embeddings, which existed like since 2003, and he also relied heavily on some work by Colobert. And what's important is that in the previous work, the process of learning word embeddings was used not as an end in itself, but in order to perform some other tasks. For example, in order to predict the next word in a sentence. So these people, Banjo and Colobert, they just used neural networks in order to learn systems which, given the first 5 words in a sentence, can predict what will be the 6th word. And in the process of training these systems, they also learned vectors for individual words, but they didn't look at them as something valuable in itself. They just wanted to predict the next word. And Mikolov made learning good embeddings, learning good vectors, just the final aim of the whole model training. So his idea was that these vectors can then be used in any other natural language processing tasks. Yeah, and it turned out that what Tuvek was very fast and very efficient, and it produced very good models. It was like, in comparison with the previous models, it was lightning fast because it used very simple neural networks, which I will describe. And yeah, as I've already said, it features actually 2 different algorithms. So there is no such a thing as what to vec algorithm. There are 2 algorithms: continuous bag of words and continuous skipgram. So what's the essence of the method? In fact, it's very simple. The algorithm is quite understandable. So first, we have a training corpus. Yeah, we have some large collection of texts on which we want to train our model. And first, we just compile the vocabulary of this corpus. We just compile a list of all the words in this corpus, a set of all distinct words. And each word in this vocabulary gets initially two random vectors. And the size of these vectors we define just at the beginning of training. For example, we can just tell the model, okay, I want my words to be represented by 100 dimensional vectors, or I want my words to be represented by 300 dimensional vectors, or whatever. So it's equivalent to saying something like, I want the semantic space of this language to be represented by 300 values. Yeah, so we predefine the size of vectors. And yeah, so each word gets two embeddings, two random initial vectors, which means that we have two weight matrices. Yeah, the first matrix is called the input matrix, WI. Let's call it, and the second matrix is called output matrix. Yeah, so I'm already talking about layers now, though I have not yet presented the architecture of the network, so you can just give it. Yeah, so the important fact is that we have one large table of vectors, which we will call the input vectors, and another large table of vectors, which are different, which we will call output matrix. Yes, and the dimensionality of both is quite similar. So the first matrix dimensionality is vocabulary size times vector size. Like, for example, if we have vocabulary of 100,000 words, then the dimensionality of this matrix, if we have a vocabulary of 100,000 words and the vector size is, for example, 100, then the dimensionality of this matrix will be 100,000 by 100. And the second matrix is just the transposition of the first one. I mean, its size is the transposition of the first one. It's vector size by vocabulary size. Yeah, so what happens next? How can we train this? Oh, oops, sorry. Yeah, so another thing. So you can imagine this as kind of a 3 layers. Yeah, so the first layer is the input matrix, then the second layer is the vector itself of the size like 100 or something like this, and the third layer is the output matrix. So it's not like a strict neural networks terminology. I'm just like trying to give some meaningful names to things. So what we do during the training? During the training, we take the training corpus and we move through all the sentences of this corpus with the sliding window, like for example, sliding window of size 10 words. Yeah, and we stop at each word. Like for example, in this example, the focus word is learning, and the window size is 1, 2, 3, 4, 1, 2, 3, 4, 8. 8 words, so 4 words to the left and 4 words to the right. These 4 words to the left and 4 words to the right are the context of the focus word, yeah, the neighbors. This represents an instance, yeah, so like each word in the corpus, each token in the corpus is an instance. We run through the corpus and stop at each instance, at each focus word. Each such instance, we look at it as a prediction problem. So we want to predict the current word from its neighbors. So like we pretend that we do not know the current word, that we do not know that this word is learning. We pretend that we know just that there is a sentence, an efficient method for something, high quality distributed vector. And we want our model to be able to predict that the real word here is learning. Or this task can be reformulated as predicting the neighbors from the focus word. It's a bit like a different flavor, but it's still a very similar task. Like if we are given the word learning, try to predict what are the 4 words to the left and 4 words to the right. It seems like, well, practically, usually humans can't predict like 4 words to the left and 4 words to the right, given only one word. But paradoxically, it's a good task from the point of view of training good distributional vectors. So yeah, the idea is quite simple. So we just want the vectors of these words in the model be such that they are good in predicting the neighbors or in predicting the focus word. And the outcome of this prediction at this particular instance determines whether we want to adjust the current word vectors or we want to just leave it as it is. So I remind you that initially each word has just random vector, just some garbage. Yeah. And then we try to predict with this garbage. Of course, the model fails. Yeah. Of course, we can't predict anything, which means that we get some mistake. Yeah. We tell the model, well, you predicted the wrong word, and then the model slightly adjusts the vector of the current word, of the focus word, for example, learning, and the vectors of these words, the context words, so that they are a bit closer to each other. Yeah. So if we imagine that this is the first sentence in our training corpus, of course we fail in predicting this word from these random vectors for these context words. And then we tell the model, okay, just make the vectors for all these words a bit closer to the vector for learning, just a bit. And then we move on to the next sentence. And then we do it just like millions of times, because the corpus is large and we can swipe through the corpus many times, not only one time. Yeah. And it seems that by these millions of small predictions and small adjustments of word vectors, we somehow come to the condition when these vectors like somehow learn to predict the focus words. Yeah, so gradually over time the vectors converge to some state which hopefully is meaningful. Yeah, so and it's important that this prediction is not like an aim in itself. It's not that we really want to predict, for example, the 4 words to the left and 4 words to the right. It's just kind of a proxy to learn vector representations, which are good for some other tasks. So just we want the vectors for semantically similar words to be similar, and this algorithm helps us to come to the same. So these 2 algorithms, continuous bag of words and continuous skipgram, are conceptually quite similar. Yeah, they differ in like a couple, well, in fact, in one important details. And I will tell it on the next slide. And both algorithms were shown to outperform traditional count-based models in different tasks. Yeah, and the difference between them is that when we are training these models, continuous bag of words tries to predict the focus word, as I said. Yeah, just tries to predict, for example, the word learning, judging from its neighbors, and skipgram does vice versa. Yeah, so it tries to predict the neighbors from the central word, from the focus word. This is the only difference between them. This is a picture from Mikolov's paper. So to the left you can see the architecture of continuous bag of words, and to the right architecture of continuous skipgram. So the idea is that we have some input. Yeah, so in continuous bag of words we have, for example, in this case the window is 2 words to the left and 2 words to the right. Yeah, so we have the vectors for the second word to the left and second word and the first word to the left, and the first word to the right and the second word to the right. We make a sum of these vectors, or we can make an average. It doesn't matter much. We can average them. The resulting vector of the vectors of the predefined vector size is used to predict the central word, the word which is missing. Yeah. We look at the result of this prediction. Yeah, we look at whether the result is good, whether we predicted the correct word. If not, if we are mistaken, then this error is backpropagated to these vectors, and they just moved a bit closer to the real word, to the real vector of this word. Yeah, and then the next time we meet the same word, we meet the same word string, the same word sequence in the text, we probably will make the right prediction. And in skipgram, it's the same, but just inverted. So we have the central word, WT, the focus word, and we just use the vector of this word to predict the second word to the left, the first word to the left, the first word to the right, and the second word to the right. And we're just adjusting our, we calculate the error as an average error on all these context words. So it seems that for some tasks continuous bag of words is better, for some tasks continuous skipgram is better, but they are both quite good. And the continuous bag of words is a bit faster, which is quite understandable because it needs to make only one prediction, and continuous skipgram needs to make as many predictions as the number of words in the context. Yeah, so sometimes people say that what What2Vec is deep learning. Of course, it is not true. None of these algorithms is deep learning. Nothing deep here. The neural networks on the previous slides are very simple, very shallow. There are no like multi-layered monsters like in some contemporary systems. So we have just a single linear projection layer between the input and output layer. And yeah, so the training objective is also quite simple. So we just want to maximize the probability of observing the correct output words given the context words. Yeah, and we do this with their current embeddings, with their current word vectors. You can think of word vectors as just like sets of neural weights in the matrices, in the input matrix and output matrix. The cost function for continuous bag of words is just cross entropy of the correct answer. Yeah, so we just calculate the log of probability of seeing the correct word given the context words. And for skipgram, it's just the sum of probabilities of predicting the correct context words given the focus word. Okay, so the learning itself, well, in word2vec it is implemented with the stochastic gradient descent, but in some other implementations the actual learning methods can be different, but it doesn't matter from a conceptual point of view. Conceptually, just the idea is that we want to predict words judging by its neighbors, or vice versa. Yeah, so once again, at each training instance, at each stop in our sliding window moving through the corpus, at each training instance, the input for the prediction is, in the case of continuous bag of words, the averaged input vector for all the context words. So we just look around the current word, average the vectors for the context words, and then we check whether the correct current word output vector is the closest to this average vector among all the vocabulary words. So like if we imagine example like the cat sits on a mat and we want to predict the word sits, then we average the vectors for the word the cat on mat. We get some averaged vector, and we just compare this average vector to the vectors of all other words in the dictionary, and see which one is most similar by cosine similarity to this vector. And if it is the word sits, then we're okay. It means that the model is good and it converged. But if it is not the word sits, then we just calculate how wrong our prediction is, just calculate how different is the probability of prediction of the word sits from 1. So we want its probability to be 1. But probably the model outputs, for example, 0.3 or something like that, which means that the error is 0.7. Yeah. And then we just propagate this error to back to the matrices of vectors that we have. And with skipgram, the input is just current word, the word sits in this example. And for each context word, we just check whether this particular context word is the most similar to the current word in the vocabulary. Yeah, and just calculate the error once again and propagate this error back, moving the vectors of the neighboring words a bit closer to the vector of the current word. Yeah, and once again, this closeness, this notion of similarity is implemented using cosine distance. Yeah, and then when we want to predict like which word is the closest one to this particular word in the vocabulary, we're just calculating the cosine similarity of the word A to all the other words in the vocabulary. We get the values like from -1 to 1 for each word in the vocabulary, and then we just turn these cosine similarities into a probability distribution using the softmax function. Yeah, so and during the training we're updating these two weight matrices, so the matrix of input vectors Wi and the matrix of output vectors, which I remind you, we initially at the start of training we just initialized with random vectors. But during this like continuous updating, yeah, these vectors get some meaningful values. Yeah, and so as a rule, just these matrices share the same vocabulary. Yeah, so we just they have the same number of rows. But then after the training is over, we usually just use the input vectors in practical tasks. So usually the output vectors is used only for training. They're kind of like technical help. Yep. So this is a quotation which I like very much. Just that during the training, the vectors of the words are kind of dragged back and forth by the vectors of their neighbors. So like each word each word vector is moved here and there in different directions by different contexts of this word. Yeah, as if there are physical strings between the word and its neighbors. But in the end, because the language is not chaotic, the language is not like a uniformly distributed system, because the language is structured, there is a structure, there is a clustering in the language. So because of that, the model finally learns like how to model the words so that it is successful in predicting the neighbors. Yeah, so this is another picture of the architecture of what2vec algorithms. Yeah, so we have input layer with the input words. Here we have the input matrix with input vectors for the words. Here we have this hidden layer which like uses the output matrix with output vectors for the words to predict the words. So you can think of the input layer as just a list of vocabulary words, and the output layer is also just a list of vocabulary words. So we have some words at the input, and we have probability distribution over vocabulary words as the output. But what is like the result of the whole training is these two matrices, is these two tables with vectors. This is what is learned actually. So after the training is over, we just take this input matrix with a list of vectors for all the words in the vocabulary, and then we use that for our downstream tasks, for some other tasks that we want. So actually after the training is over, we just drop all of this and use only this matrix of the size vocabulary by the vector size. Yeah, by the way, this is a very useful demo, like a web service, which I like very much, which you can use to visually see just how what2vec training works. You can open it in your browser and just play with it. It's quite interesting. You can see actually how the neural weights are updating. Yep. So what2vec was very successful, and in the following years there was lots of follow-up work. So people quickly started using it very extensively. So like folks at Stanford quickly released the thing which they called global vectors, or GLOV, like a bit different approach to learn what embeddings. Then there was some excellent research work showing that actually what continuous skipgram does is that it implicitly does the same thing that the count-based models do. So it implicitly factorizes the word context matrix of PMI, which is quite interesting. So these people just showed that actually these methods are not as different as they seem to be. Well, the same people then lots of people analyzed why what2vec is so good, what's the reason for this, for its performance. That sometimes it's just because of a smart choice of hyperparameters. Then Mikolov afterwards proposed a paragraph vector, which is an algorithm which learns distributed representations, which learns embeddings not for words, but for documents, for paragraphs, for sentences, for like whatever sequences of words. Then Facebook bought Mikolov from Google. So now he's still at Facebook. Already after moving there, he released a fast text tool, which learns embeddings not only for words, but for subword elements, for character sequences, which allows you, for example, to infer an embedding to infer a vector for some word which is not present in the vocabulary of the model, based on its form, yeah, which is especially important for morphologically rich languages, where we have lots of words which are just forms of one and the same word, like for example, like, yeah, and which means that there are lots of words which are quite similar in meaning and similar in form, which is not the case for English, for example, because English is a morphologically poor language. Yeah, so there was lots of follow-up work. So nowadays lots of people work on these things. All these approaches were implemented in many open source systems which you can use freely, like GenSim, TensorFlow. All of these systems have implementations of many of these algorithms. Yeah, so this is yeah, just one example of this follow-up work. This Stanford algorithm called GLOVE is quite interesting in that it attempts to combine the success of count-based models and prediction models. So they still compile this large co-occurrence matrix, but then they just stochastically sample non-zero values from this matrix and use machine learning to produce such vectors that such vectors for word pairs that the dot product of this vector just equals the logarithm of the word's probability of co-occurrence. So we have two words, A and B, and they just try to learn such their model tries to learn such vectors for A and for B, that the dot product of these vectors is the same as the log probability of these words A and B co-occurrence in the training corpus. And yeah, this model seems to work also quite nice, and for many tasks it outperforms What2Vec. For some tasks, What2Vec outperforms GLOVE. Yeah, so and yeah, you can easily download the code and the pre-trained models from Stanford website. Yep. So what's important is that nowadays probably the most widely used application of word embeddings is that they are replacing the discrete word tokens as an input to other neural networks. So nowadays, of course, nowadays people use all kinds of complicated artificial neural network systems to solve NLP tasks. Yes, they use like feed-forward neural networks, convolutional networks, recurrent networks, LSTMs of all kinds, and many of these systems want sequences of words as an input. But it seems that we can replace these discrete words, discrete like sequences of characters, with meaningful word embeddings, with meaningful word vectors, and then all the systems all of a sudden start to perform much better. Yeah, like this is a nice schema. Yeah, like we have some neural networks which does something, which, well, it outputs some prediction. We don't care whatever what it is, what is the particular task. And at the input, we have some words, yeah? And imagine that we have already pre-trained some good word embedding model, some good distributional model, which tells us what is the vector of this or that word. And we just replace the words with their vectors, with their word embeddings. And then we feed these word embeddings to our neural network, which does something, whatever it is, like syntactic parsing, sentiment analysis, whatever, and it outputs its prediction. And it seems that it's much easier than for these neural networks to do its task if its input is some meaningful word embeddings, because the model now just knows from the start which words are similar and which are not. Yeah, this is another example. Like, for example, yeah, we have some very complicated long short-term memory neural network which tries to predict sentiment of a sentence, like whether it is positive or not. And we have a sentence like a goodbye. Yeah, and instead of this LSTM system like trying to discern what does the word good mean and the word bye mean, and instead of this system trying to train on particular words, we just replace these words with their embeddings, and then yeah, the system just knows that, for example, a goodbye and for example, a sentence an excellent bye, that these sentences are quite similar, because good and excellent will have similar vectors. Yep. So, and some final remarks about how can we evaluate models. Yeah. So evaluation is the cornerstone of natural language processing, and of course, after we have trained our distributional model, we want somehow to make sure that it is good. We want some way to compare different models against each other. We have some way to tell that this model is just gibberish and this model is excellent. It's difficult, in fact. Evaluating is difficult. It's a subject of like special workshops at major NLP conferences. And there are several ways to do this. You can, for example, create some gold standard sets of word pairs with some manually annotated measure of semantic similarity between these word pairs. And then we can just make our model to output its prediction for the similarity between these word pairs, and then just calculate how it correlates with human judgment. Yeah, just for example, humans tell us that tomato and cucumber are similar, for example, like 8 points out of 10, and our model tells us that tomato and cucumber are similar with the cosine similarity of like 6 points out of 10. So, well, quite similar. But if, for example, for some words, human judgment is 10 out of 10, but the model outputs like 2 out of 10, then something is wrong with the model. Yeah, we can ask our model to do synonym detection, like also compare it against some gold standard set, which tells us which word is the most similar from this set of words. Like we can ask our models to do concept categorization, like try also once again comparing it against some manually annotated clusterings or groupings of words. We can do analogical inference. There are analogical data sets, like with the questions like, for example, Oslo is related to Norway as Stockholm is related to what? And we can ask our models to answer such questions, and just we can measure how good they are in this. Yeah, and there are lots of other suggestions on how we can evaluate our models, lots of literature on this. Yeah, but in the end, of course, people in practice just evaluate their model on their models on their downstream tasks. Like we use this model, for example, like I've shown on the previous slide, in sentiment analysis. So yeah, we have some system which performs sentiment analysis, and it accepts word embeddings as an input. Well, okay, we just use try different word embedding models and see whether they help our system or not. And based on that, we just decide which model is good for us and which model is bad for us. Yeah, and the performance of distributional models can depend very heavily on some hyperparameters which we choose when we train these models. For example, this plot shows just how the performance, the accuracy of the model depends on the size of the vector and on the size of the window. Yeah, so on the vertical axis we have the accuracy, well in this case not accuracy but the average precision, but well it's just the measure of how good the model is. And here we have the size of the vector in the model, so whether our words are represented by 50 dimensions, 100 dimensions, 300 dimensions, and so on. And different colors just reflect models trained with different window size, so with different context width. Yeah, so it can be seen from here that increasing vector size usually helps, but after like 500, the improvement stops. Yeah, so it doesn't make much sense to increase the vector size after 500. And usually people say that like 300 is something like sweet spot. Like 300 is some saying default in training distributional models. Yeah, and it seems that at least on this particular task, the narrow window of one word to the left and one word to the right is the best. Yeah, so for this particular task, narrow windows are better. For some other task, large windows might be better. Yes, so and some frameworks and toolkits that you can use. So Dissect is a library developed at the University of Trento, which deals with count-based models, which is quite good, and you can use it if you want to play with count-based models. Yeah, you can certainly use the original C code of Bot2Vec. Yeah, you can download it, compile it, and play with it. Yeah, modify it if you want. If you speak Python, then you can. Then it certainly makes sense to use GenSim library, which implements Bot2Vec and fast text in Python, which is quite fast. It has wrappers for many other algorithms, so it has lots of features, and I highly recommend it. If you prefer TensorFlow, you have Bot2Vec implementation there as well, along with their own distributional models. Like Google developed something called Swivel, if I remember correctly, which is another kind of distributional algorithm. Yeah, you have the reference implementation of GLAF and lots of other toolkits and libraries that you can use if you want to play with distributional models. Yep. And it's important to understand just in what formats the models can come to you. So if you build some natural language processing system and you want to use word embeddings, you want probably to not to train the model yourself, but just to download some pre-trained word embeddings from someone else, which is quite reasonable. And then it's important to know just in what format the models can come to you. Yeah, so it can be like they can be in simple text format, just a simple text file with the values of vectors and with the words. So just one word per line, a word, then a sequence of values of the vector which corresponds to this word. And usually the first line gives information on the number of words in the model and the vector size, like 100,000 words, and the vector size is 300. Also, sometimes people can binarize these text files, which means they like take less space. There is also a special format in GenSim, which uses NumPy matrices, and it's better in that it stores a lot of additional information about how the model was trained. So if you save model in GenSim, then later you can load it and see just how it was trained, what was the vector size, what was the window size, and so on and so forth, and you can continue training after that. Yeah, so you can use GenSim to work with all of these formats, so it's quite convenient. Yeah, and just finally a bunch of practical observations. Lots of people use Wikipedia as a training corpus, and it seems that it's not maybe the best choice because, like, of course it's available and it's good. Like everyone can download Wikipedia and train model on it. But it seems that probably it's just too specific language, and like the performance of the models trained on Wikipedia fluctuates very much, and like you can't really rely on it. Also, it helps to normalize your data, just to lowercase the words in your training corpus, to lemmatize them, to probably detect named entities and merge them into one token. You can augment your words with part-of-speech tags, like transform the words into this form, boot underscore noun, boot underscore verb, so that these words get different vectors, because in fact they're different words. And in many languages like English, many words are ambiguous from the point of view of their parts of speech. So probably you want to first like pre-process your corpus and assign each word part of speech tag. It helps to remove stop words like prepositions, articles, all that stuff, because you don't want to learn vectors for them anyway. Yeah, and there is some statistical downsampling for this in the original bot2vec, but it seems to work like worse than just removing stop words according to all stop words according to some list. Yep, and yeah, it's just also some practical advices which only make sense if you want to train your own model. Okay, so I will skip the part about representing documents. I suppose the slides will be online, so you can later see it yourself if you want. Yeah, so, and just to sum up, what embedding models are kind of like nowadays employed in almost every natural language processing task that you can imagine. They provide us with meaningful word representations, yeah, which you then can use in whatever way you want. And we have lots of tools which you can employ to play with these models. There are lots of pre-trained word embeddings which you can download and use, play, yeah, and that's it, I suppose. And if you have any questions, I will be happy to ask them in the remaining 2 minutes. Thanks. Okay, if no questions, then I suppose we can wrap up. Thank you.